Now see a dual nature of radiation. We have done light, we have done light in the form of the ray, waves and particles. We have seen many phenomena of the light, like this is here reflection, refraction, interference, diffraction and polarization. See here, all these phenomena can be explained by assuming light is travelling in the form of the wave. But when you explain like this is your photoelectric effect and also Compton effect, these phenomena cannot be explained by using the wave theory. So, we explain these phenomena by assuming the particle nature of the light, particle nature of radiation. So, we can assume sometimes light is in the form of the wave and light is in the form of the particle. So, we can say the light has, or you can say the radiation has got dual nature. Now, let us see the example of the photoelectric effect. You cannot explain photoelectric effect by using the wave theory. See one example here. If you assume light is in the form of the wave, so when you increase the intensity, it means the energy of the waves are increasing. It means when the intensity of radiation is falling on the metal plate, so energy of the electrons should increase, but it does not happen in case of the photoelectric effect. So, wave theory cannot explain this one. And after that, that is why we here the Einstein assumed that the light is travelling in the form of the photons or the particles and photoelectric effect was explained. Now, see here another point is here in this case, this dual nature of the light or the radiation was explained by the de Broglie. So, there is a de Broglie hypothesis. According to de Broglie hypothesis, any moving particle behaves as a particle as well as wave, and the waves associated with the moving particles is known as matter wave. So, we can say any moving particle can behave as a wave. Now, see here about the photon, we know according to Einstein's energy of the each photon, that is E is equal to given to you h nu. Suppose photon is assumed to be made of the mass m and its speed is c. So, we can write E is equal to mc square according to Einstein's mass energy relation. So, these two energies should be equal. So, we can write mc square is equal to h nu. So, m is equal to h nu upon c square. Now, the momentum of this, the momentum of the photon we can write here, p is equal to, that is a momentum, that we can write here velocity, that is a c into m mass. So, we can write here p is equal to c into h nu upon c square, this and this will get cancelled. So, we will be getting p is equal to h nu by c, that is p is equal to h by lambda. So, here we can write in this case here p is equal to h by lambda. So, lambda is equal to h by p. This is the wavelength of the light or the particle moving here, and so we can say the matter wave or the wavelength of the matter wave is given by lambda is equal to h upon p, where h is here Planck's constant and p is momentum. If there is a particle of mass m and moving with velocity v, then we can write here lambda is equal to h upon mv. So, this lambda is known as here in this case, that is the de Broglie wavelength. So, lambda is called de Broglie wavelength. And now, here if suppose you are taking v is equal to 0, so lambda will be infinite here, and if the v is equal to infinite, lambda will be here 0. So, you cannot observe the wave in these cases. And also see here the de Broglie wave or these matter waves are not electromagnetic waves, because electromagnetic waves are produced due to oscillation of the charged particles. But here there is not necessarily the charged particle, any particle can move and the wave is associated with that moving particle is known as de Broglie wavelength. Now, we can do many relations here to calculate de Broglie wavelength in the different terms.